Okay, good morning. Last time we started discussing the chamber process, and I'll complete that, and then we will move on to the contact process. You may be able to recall the mechanism that we talked about, how NO and NO2 play a very important role in catalyzing the oxidation of SO2 to SO3. A crucial equilibrium which was mentioned last time was this: that's nitrosyl sulfate reacts with water and it forms sulfuric acid plus NO2 plus NO. It's in this process that the NO2 is partly getting reduced to NO, and the SO2 is basically getting oxidized to SO3, and it's forming H2SO4. So you form NO2 plus NO. So this NO, of course, has to be reconverted back into NO2 to sustain the entire process. That's basically what one has to do. That we said is the rate limiting step in this particular case, but this is much faster than the oxidation of SO2 to SO3. Even though this is a rate limiting step, the NO going to NO2, it's a lot faster, and that's why this is catalyzing. The NO2 is catalyzing the oxidation of SO2 to SO3. You will be able to see the ingenuity of this particular process, which was actually in vogue well into the, I think, into the 40s. Even though the contact process has been practiced for a long time, but it is not as if the chamber process had altogether disappeared. The chamber process was considered to be a pretty good process, and at one time they were going hand in hand. And it's a process that has lasted what, maybe about a century. So let us try and understand how ingenious they were in making use of this equilibrium. This is another thing that more than any of the other processes in those days, I'm talking about a good close to about 150 to 200 years ago, that mechanism was important. And if you understood the mechanism of a reaction, then it could help you in design. But if you don't, you're just shooting in the dark. Let us try and understand what was this chamber process. First is that either you can start with iron pyrite or a source of sulphur, and then you need air. Basically, you have to oxidize the sulphur to SO2. That's the first thing. That's what is going on over here. We know that it's a highly exothermic reaction, and that's the reason why they were air cooling it. So they were allowing air to pass through and cooling the stream, because otherwise it was too hot. Okay? Now, they were doing something else in those days. You remember that they were using Chile saltpeter. That's what Glover did. But today, of course, one wouldn't necessarily take saltpeter. You may actually start with ammonia and oxidize ammonia to NO2. So that would be the catalyst, which would also go along with the SO2. Or in earlier days, of course, they were using the what is called the niter pot, Chile saltpeter nitrate, sodium nitrate. That's what they were doing, and it was decomposing and forming NO2. We know that the NO2 catalyzes the oxidation of SO2. We also know that when you are passing air through this, that air is being utilized to supply the oxygen for the oxidation. But all of the oxygen is not necessarily consumed in this first part. So there will be quite a bit of oxygen which is passing through in the outlet, besides, of course, nitrogen, which will always be present in air. Now, what they were doing over here is this is known as the Glover tower. The SO2 stream, along with your NO2 and along with oxygen and etc., were going through this tower. It's a counter current flow, so the gases are traveling up, and we will explain what is there in the chamber acid. You'll see chamber acid mentioned here. the chamber acid was effectively a weak sulfuric acid, which had more water and less sulfuric acid. So they were passing this through that. Now, what then happened was that we were in a situation where we were in the left-hand side of this equilibrium, and so because there's quite a bit of water, and we will discuss what else is coming over here. There is another component which is coming here, which is the nitrated acid of this stuff, and I'll explain to you where it's coming from. So you had this stuff, you had some sulfuric acid, but there's quite a little bit of water from the chamber acid, and so these were reacting and forming more sulfuric acid, and so a weak sulfuric acid was getting converted into a strong sulfuric acid, over here. Finally, that strong sulfuric acid was going into a container, and this sulfuric acid concentration is roughly about 78%, concentration. When this reaction took place, the equilibrium, in other words, shifted to the right, I formed NO2 and NO in the free state, not as a bound nitrosyl sulfate. So that, along with my air, the oxygen in the air plus the nitrogen, were being taken to these chambers, which are known, these were the lead chambers. That's the lead chamber process, or that's what the chamber process is. In the chambers, what was happening is that again the SO2 oxidation to SO3 was being catalyzed, because there is already NO2 present, plus there's NO. As this oxidation goes on, what will happen is that you'll build up more and more NO, and in the presence of the oxygen from the air, the NO again reconverts to NO2. Although it's the rate determining step, it does occur. So you're forming SO3, and from the top you're spraying water. So that water plus the SO3 which is formed is going and forming a weak sulfuric acid, and this is known as the chamber acid. It's not as if they had only one chamber. There would be still residual SO2 which has not reacted. So that is fed into chamber 2. Again, there will be some amount of reaction that takes place here, and again some SO2 goes to SO3, and again spray of water, again sulfuric acid. Not enough, they again put it through a third one. Traces of SO2 which are still not reacted, they will begin to react in this last chamber, and by the time it exits from the third chamber, pretty much all your SO2 has got converted into H2SO4. Okay. So first this reaction took place, the reaction between the chamber acid and the nitrosyl sulfate, and it formed sulfuric acid, and the concentration of sulfuric acid increased. It went into this container, okay, and the SO2 and NO2, etc., they were effectively whatever was left was brought in here, and then the successive oxidations took place. Now, this tower is known as the Gay-Lussac tower. So I hope you can see that there were very great minds who worked on these things, starting from Glover. We don't know actually about their contributions in these kinds of things, but they developed fantastic technologies. Now, here what happened was that what is coming out, because all my SO2 has effectively got converted into SO3 and become chamber acid, sulfuric acid. What will exit from here is really my NO2 and NO. It's done its job. Okay? So it's coming out from here. When it comes out from here, you are not just letting it escape into the atmosphere. What you're doing is, now this acid has become concentrated after the this tower acid, partly because of this and partly because of the chamber acid. So both of them together increase the amount of the strength of the sulfuric acid. So this is concentrated sulfuric acid. Now, so what you're doing is, this sulfuric acid, you're pumping to the top of the Gay-Lussac tower. And from the bottom, your NO2 is traveling up. So because it is concentrated acid with low amount of water, so now the reverse reaction will take place. In other words, I will form nitrosyl sulfate and I will prevent any NO2 from escaping into the atmosphere. And that's how NO2 becomes catalytic, because I can recycle it. Okay. Of course, there will be small amounts of losses. So the losses that you have, that effectively is what you will be feeding through the combustion of this nitrate pot or ammonia. So there will be some loss, no doubt. And so to that extent, I'll top it up with more amount of NO2. Otherwise, the NO2 is just getting recycled because of this Gay-Lussac tower. What happens to it then? It became nitrosyl sulfate, nitrosyl sulfuric acid. Now what you're doing is that you are pumping this into the glower tower. So that is this part which you are pumping. And from here, your gases came and some amount of SO2 would have got oxidized to SO3 in presence of the NO2, etc. by the time it reached the glower tower. So that SO3 plus the stuff from here, plus the sulfuric acid from the chamber acid, those are all the sources of my sulfuric acid. So again, the nitrosyl sulfate decomposes here because of the reaction going forward. Again, it releases NO2NO, which goes in over here along with fresh amount of SO2, etc. And this process goes on and on. Is that clear to everyone? The chamber process?
Yes, sir.
Okay. Now, one more thing that you must know is these chambers, these lead chambers were massive. In fact, you all gave some good reasons as to why there is lead. Okay. But another reason, of course, is that, as many of you said, that lead could be formed in the form of big reactors in those days. And don't forget that we have to dissipate heat, because when the water is coming and there is sulfur SO3 over here, and it's forming sulfuric acid, it's very hot because it's an exothermic reaction. The metallic nature of the reactor helps to dissipate the heat, and also because of the passivation of the lead surface, obviously the sulfuric acid does not chew up the reactor. So those would be all the advantages of the of lead. Today, of course, people tend to shy away from lead because lead has been shown to be quite a toxic element. Although in its metallic state that may not be the case, but there will always be some amount of degradation, corrosion, and therefore there will be some amount of lead that will leak through. Okay? So this is basically the chamber process, the one preceding the contact process. Do you see any disadvantage? To me, it looks very elegant. Any disadvantage that there might have been?
So the NO2 and NO forming, nitric oxide and nitrous oxide forming.
Forming? You are
Yes,
saying
sir.
that those can be a bit dangerous?
Yes, sir. So they may hinder the process, sir.
Yeah, so there is always a little bit of a fear of explosion, although it seems to have been a perfectly safe process, But yes, to the extent that you have got NO and NO2 and that has to be managed. Of course, if you could do without it, that would be always the best thing to do. But no doubt about it that this was a very ingenious design. But as you said, I mean, it will never be 100% complete, this reaction. So some amount will definitely escape into the chimney. Okay, so you're right. What kind of a reaction is this? What kind of a catalysis reaction is this that is occurring here? The SO2 and the NO2, they are where? In which phase? Solid, liquid, gas. Which one?
Yes, sir.
Right. This is a homogeneous catalytic reaction that is taking place in the gas phase. Of course, to the extent that you are spraying water and some amount of you can see that how beautifully they were driving the equilibrium forward, because they were just forming sulfuric acid and it was coming out. So they were sweeping out the product and driving the equilibrium forward. But the effective reaction was taking place in the gas phase. Because the SO2 largely would have been in the gas phase, and so would the NO and NO2. Now, let us look at one more gas phase reaction, because what happens is, there is a tendency whenever we talk about catalysis to either talk about the liquid state or about liquid solid or gas solid, heterogeneous catalyst, solid catalyst. Okay, very few people talk about gas phase reactions, and yet they are very important. So we have seen how important the chamber process was, and it's a homogeneous gas phase reaction. Okay. Similarly, another very important gas phase homogeneous catalytic reaction is what takes place in the upper atmosphere. And I just thought I'll mention it, although it's got nothing to do with the sulfuric acid production. Now, all of you know that there has been a huge problem of a hole in the ozone layer. One of the things that was implicated in this burning of the hole was chlorofluorocarbons, CFCs. This is like a CFC. These are, you can say, the 3 chlorine atoms. If you take something like CHCl3, okay, chloroform, or you could take CFCl3, things like that. Now, what happens is that this stuff in the upper atmosphere, because there is the maximum concentration of ultraviolet radiation is there in the upper atmosphere. So in the presence of the UV radiation, this stuff, it undergoes a radical reaction. It basically just breaks up and generates a chlorine radical, Cl dot. So the ozone which is there in the upper atmosphere, that ozone is broken down by the chlorine radical. So effectively, what happens is that it will form, you can imagine it will form O and O2. So this is your O2, and there will be an O radical, that is this O. Now this O2 which is formed and this O radical which is formed, now this O radical plus the Cl radical ends up forming ClO. Or you can just show it over here so that it forms O2 plus ClO. Okay, it's just been kept here so that it's easier to understand. So you get O2 plus ClO. Now this stuff reacts with another molecule and it forms O2. So again releases the Cl dot. The Cl dot can again react with another ozone, and the ozone reaction can be catalyzed, the degradation by the CFCs, which in turn is generating the chlorine radical. This is the reason why CFCs were banned. Of course, CFCs were very important in refrigeration. They were used, and even today, some of the fridges, etc., will have CFCs, although they have been largely phased out. This is probably the most important gas phase catalytic reaction that takes place in the world, and takes place day in and day out. This stuff. Take another example of a gas phase reaction. For example, tertiary alcohol. It's a liquid, of course, but if I heat it up, it will form a gas. And so in this particular paper, they've taken gas phase tertiary alcohol and they introduced hydrogen bromide, again, which is in the gas phase. And so they are having a gas phase homogeneous catalytic reaction. And this is a theoretical calculation of the entire catalytic process that takes place. But the sum and substance is that they were generating effectively the olefin, through the dehydration of the tertiary alcohol. That's effectively the reaction. Gas phase reactions, as I told you, are not taught so much, but you will see these as important examples. I was reading an article, The Beginnings of Industrial Catalysis. So I've just added heterogeneous here because it's not true. We talked about the chamber process, which was a catalytic process, catalyzed by NO2 long before somebody said beginnings of industrial catalysis. That was an industrial catalysis and of the biggest molecule at that time in volume, which was sulphuric acid. But what they are basically referring to is heterogeneous catalysis, and that's what the contact process is. It's worth mentioning a little bit about the birth of these reactions. Now, why it is so important and why I'm stressing this is, although we know it is catalysis, that word catalysis and the meaning catalysis had still not been stated. These were all looked at as curious phenomena. They were not looked at as, oh, these are catalytic processes. Nobody knew what is a catalysis at that point. Now, who were the people who did extraordinary work? One of them was Sir Humphrey Davy, whom you have heard of. He was the one, and he said something very interesting. And he's reporting his observations at the Royal Society in 1817. And he said, I had intended to expose fine platinum wires to oxygen and olefinate gas. So basically olefins. And to oxygen and hydrogen during the slow combination under different circumstances, when I was accidentally led to the knowledge of the fact and at the same time to the discovery of a new and curious series of phenomena. What was that curious series of phenomena? That hydrogen and oxygen got together and became water. That these things, the olefins, basically got transformed into other organic molecules in the presence of platinum. And otherwise it didn't happen. This, no doubt, motivated others to start looking at, these were curious phenomena. There was no need for this. There was no utility of these reactions. It was just discovery. Whereas SO2 to SO3 was an important process. People knew that there are certain shortcomings of the chamber process, like the escape of NO2. And so, can we do without it, as one of you so nicely said? And that's exactly what happened. Once this phenomenon had been found, that you pass gases, etc., in the presence of some platinum, and some curious phenomena takes place, that this person, Peregrine Phillips, in 1831, so you can see it's about, what, about 14-15 years after Humphrey Davy's work, that he was smart enough to ask the question, hey, what happens if I just introduce SO2 and O2 instead of putting hydrogen or olefinate gas? Otherwise, I'm doing everything the same. What would happen? Will it get oxidized to SO3? And he took out the patent in 1831. And you can see the title of the patent is Certain Improvements in Manufacturing Sulphuric Acid, commonly called oil of vitriol. I actually got his patent and I've taken it from the patent. So let's read what he says. And remember, such things did not fall from the sky. I repeat, someone had to discover them, someone had to invent them. And usually it was on the back of somebody else's work. Peregrine Phillips on the back of Humphrey Davy's work. But always somebody did something and somebody then took it forward. It's very interesting. So let's read it. The first improvement then, namely the instantaneous union of sulphurous acid with the oxygen of the atmosphere, I effect by drawing them in proper proportions by the action of an air pump or other mechanical means through an ignited tube or tubes of platina, porcelain, or any other material not acted on when heated by the sulphurous acid gas. In the set tubes or tubes, I place fine platina, just like in wire, or platina in any finely divided state, and I heat them to a strong yellow heat, and by preference in the chamber of a reverberatory furnace. Okay, reverberatory furnace is wherever I'm doing heating indirectly. I'm not introducing the fuel along with my substrate and burning it and doing it. So I'm just getting the heat, but I'm taking the heat indirectly. That's what you do in a reverberatory furnace. And I do affirm that sulfurous acid gas being made to pass with a sufficient supply of atmospheric air through tubes as described, properly heated and managed, will be instantly converted into sulfuric acid gas, which will be rapidly absorbed as soon as it comes into contact with water. In other words, Peregrine Phillips dispense with NO2. Mind you, this is the contact process. When we ask, hey, what is contact process? And you'll say, hey, it's this and vanadium pentoxide. Vanadium pentoxide was just a replacement of the catalyst. That was not the original contact process. This is the contact. And this is the original contact process. So if you ask who invented the contact process, it is Peregrine Phillips in 1831. What did BASF do? Around 1898, at the turn of the century, BASF found another catalyst, which did the job of platinum, and we will try and understand what was so important and significant about it. But it was only another catalyst. It was not the original discovery of the contact process. Is that clear to everyone?
Yes, sir.
Okay. Now, let's now say, firstly, why was there so much of interest in the contact process, and probably even Peregrine Phillips has not said that, but certainly BASF did. One of the shortcomings of this process was that the acid that you got was not like oleum, it was 78% sulfuric acid. I mean, not even concentrated sulfuric acid, forget oleum. There were certain reactions which you could not do with this acid. So there was a need to try and make sulfuric acid with a higher concentration. And when you do that, always look at the theoretical limit. Okay, that if I have to contact SO3, and let's say I get 100% SO3 and I add water, then what would be my concentration of sulfuric acid? It would be 98%. Typically, as you know, when we say today's concentrated sulfuric acid, we are talking about 98% sulfuric acid. But that's what it is. It's not 78. So it's always good to know what is the theoretical limit and how far am I from that. And obviously, then you try and strive to achieve the theoretical limit. What happened was, that was the time, World War I, there was a lot of ammunition, bombs, this, that were being produced, and nitration reactions which required concentrated nitric acid, concentrated sulfuric acid, along with nitric acid. Sulfonation reactions, because dye industry was flourishing, and many of the sulfonation reactions, especially of very electron withdrawing aromatic systems, it was very difficult to do otherwise, unless you required oleum to do that sulfonation. So many of the sulfonation reactions were with oleum, and so there was a need for concentrated sulfuric acid. That's really what the contact process was able to cater to, which the chamber process could not. That was actually probably the most important reason, rather than NO2 safety, this, that. They were actually secondary. the most important was the inability to make concentrated sulfuric acid. So primary impetus for the development of the contact process came from a need for high strength acid and oleum to make synthetic dyes and organic molecules. The contact process employing platinum catalyst began to be used on large scale for this purpose late in the 19th century. So Peregrine Phillips invented it in 1831, but it was only around 1880, 1890 that it really started being used, the contact process. Its development accelerated during the World War I to provide the concentrated mixtures of sulfuric and nitric acid for the production of explosives, dynamite. Okay, so effectively, these were the impetus for a new technology. Having introduced you to both homogeneous catalytic reactions and heterogeneous catalytic reaction, which was Peregrine Phillips in 1831. Now let us see, when the word catalysis and when what it is meant was first articulated. And as I told you, it was articulated by Berzelius. Berzelius used to sit at his desk, basically read a lot of stuff, and he would enjoy correlating things, Someone has reported something, somebody has reported, they all otherwise looked all disconnected stuff. The people, the greatest minds, are people who can look at all kinds of stray observations and put them together, and then come up with some great things. How do we know what Berzelius really did? When I was reading the Nobel lecture of Oxford, 1909, this is what Oswald says, paying tribute to Berzelius as the person who is the one who proposed catalysis. And he says, the processes grouped together by Berzelius were one, and all of these today you take for granted. The transformation of starch into dextrin and sugar by acids. So just the hydrolysis of starch. The same transformation by malt extract. The decomposition of hydrogen peroxide into water and gaseous oxygen in the presence of platinum, manganese dioxide, etc. Another great mind, Thenard. The action of finely divided platinum on inflammable gas mixtures, Humphrey Davy, 1817 you saw. And the formation of ether by the action of sulfuric acid on alcohols. You cook up primary alcohols with acid and it forms the ether. That's how you'll make diethyl ether. Of course, there are other ways of doing it, but that's the easiest. So he was able to take all these kinds of things. Till at that time they were just considered as curious phenomena. And he was able to see some kind of commonality, among all of this. And finally, this is what Berzelius said. 1836, mind you, 1817 Humphrey Davy, 1831 Peregrine Phillips. So catalysis had been worked upon before the word was articulated. He is the one who basically said what was already known. It is not that he did the first catalytic reaction. Certainly not. Okay? And this is what he said. It is then proved that several simple or compound bodies, soluble and insoluble, have the property of exercising on other bodies an action very different from chemical affinity. By means of this action they produce in these bodies decompositions of their elements and different recombinations of these same elements, to which they remain indifferent. That is what catalysis is. At the end of it, the catalyst is not there in the product. Reactants are getting converted into product and the catalyst is remaining indifferent to them. Okay? That's basically what catalysis is. And So this was the first articulation of catalysis based on all the great stuff which had been done by great minds before that. Now let us see, we are moving from the platinum based contact catalyst to the vanadium pentoxide based catalyst. In 1915, and mind you, 1915, although some of the original work had been done at the end of the 19th century, but really it was in the early part of the 20th century that really the process began to get commercialized. Interestingly, the Haber process and the sulfuric acid contact process based on vanadium catalyst, more or less around the same time, these things happened. And by who? BASF. I mean, what a great company. In 1915, an effective vanadium catalyst for the contact process was developed and used by Badisch in Germany. This type of catalyst was employed in the United States starting in 1926, even then about 11 years later, and gradually replaced the platinum catalyst over the next few decades. In other words, the platinum catalyst was on for at least 40-50 years. It was there. You might say platinum catalyst contact, of course. Why was the vanadium catalyst so revolutionary? Okay. Vanadium catalysts have the advantages of superior resistance to poisoning and of being relatively abundant and inexpensive compared to platinum. Usually, if one thing is good, we say महंगा है मगर performance अच्छा है. But who would say सस्ता भी है, performance भी better है? That is what vanadium catalyst does. Just so remarkable. The sheer compulsion of replacing the platinum catalyst with a less expensive catalyst, more abundant, less poison, is what pushed out platinum ultimately, and vanadium pentoxide became increasingly more popular. Let us look at the massive role that catalytic processes have had, starting with platinum for SO2 to SO3 from peregrine Phillips. Today, I think it would be impossible to imagine life without these heterogeneous catalysts. Whether you are talking about crude oil, a crude oil cannot be used directly. You have to crack it, you make it smaller, those molecules. That's what zeolite catalysts do. All the crude oil comes with all this sulphur, etc. You have to knock it off, and nitrogen. You have to do treatment with hydrogen and make sure that all the nitrogenous and sulfur species are driven off in the form of H2S, ammonia, etc. And that's when you'll get something which becomes worthy to put in your vehicle. Okay? Naphtha, these things have to be reformed into the desired kind of structures that was most suited for different kinds of vehicles. So reforming of naphtha to gasoline was so vitally important, to get also the anti-knocking properties. Okay. Alkylation, ignored the sulfuric acid and HF because these are not solid catalysts. But today, one of the biggest thrusts is can you look at catalysts which are solid, not very different from aluminium chloride, but AlCl3 has a lot of problems in workup. But if you could even overcome those and do Friedel-Crafts alkylation with other kinds of solid catalysts, and there are things which are known, that would be a great, great thing. Polymerization, you just see the hundreds of millions of tons of polymer being produced every day. And through the Ziegler-Natta catalysts, which are based on titanium and zirconium and stuff like that. Ethylene, epoxidation, the countless surfactants, etc., other molecules which are made from epoxides, from ethylene oxide, and it's all by silver catalyst. Later on in the course, we will of course be looking at some of these in detail. Vinyl chloride, all your piping, PVC piping. You cannot imagine today piping which is not PVC. It's so huge, so vast. Steam reforming of methane. This is what Haber-Bosch process was all about. It's not really about N2 plus H2 going to NH3. You have to first get the hydrogen, and that hydrogen came from the steam reforming of methane and with a nickel catalyst. And there also you had the water gas shift reaction, which was another very crucial reaction. This reaction, which will probably increasingly become important in the years to come, is if I can reconvert carbon dioxide with hydrogen, maybe generated through electrolysis of water, and if you can convert back into methane. Once I've got methane, then the sky is the limit in what all I can make. I can make anything from methane. Ammonia synthesis with iron catalyst. Ammonia oxidation, the Ostwald process with platinum rhodium. Acrylonitrile, hydrogenation of vegetable oils, dalda, was one of the biggest applications in the food industry. Hydrogenated vegetable oils. Sulphuric acid, what we're talking about, vanadium pentoxide. And all your vehicular emissions today, which you are trying to contain so that the SOx, NOx, etc. doesn't get released into the atmosphere. And these are the kinds of catalysts which basically take care of it. Either it's converted into nitrogen, or into something very benign. And that's what you do in the car exhaust. So I hope you can see the array of catalysis, and not always remember the first one, which was the work of Peregrine Phillips. When we are looking at heterogeneous catalysis, we need to consider a few things. Like, for example, in the contact process, we are really talking about a gas-solid reaction. You can actually break it up into 5 different steps, things that have to happen. First, of course, whatever are your reacting gases, they have to diffuse towards the catalyst because it has to finally react at the surface of the catalyst. Okay? Then the gases will have to get adsorbed on the surface of the catalyst. Third, there must be a chemical reaction that takes place on the surface of the catalyst. Usually, we tend to stop here. But these are equally important. After the reaction, the products have to dissolve. They have to come out of the catalyst surface so that again fresh reactants can go in. So desorption is as important as adsorption. And the fifth is that not just dissolve, because you have to maintain a concentration gradient. So it must diffuse away, and that's how you will always have a depleted concentration of products close to the surface, and so that continuously the reaction will take place. Because otherwise, if the products are just hanging around near the catalyst, maybe the equilibrium is not going to get driven to the right. So these are the 5 things that you need to understand. We all know that catalyst, what it does is really it lowers the activation barrier for a reaction. That's effectively what it does. Okay? And different catalysts act in different ways. So the mechanism by which they act could be different. And they may lower the activation barrier to different extents. May not be to the same extent. Like platinum and vanadium pentoxide, both of them will give you, from SO2 it will give you SO3, but need not be by the same mechanism. Just to illustrate that, I thought I will stress this, it's very interesting. Just see what it says. It has been observed that the rate of oxidation of SO2 on the surface of platinum catalyst is proportional to the pressure of SO2 and inversely proportional to the square root of the pressure of SO3. That means the more amount of SO2 I can push, the faster the reaction will be, and I need to take out the SO3 efficiently because SO3 is going to inhibit the process. because it's inversely proportional to the square root of the pressure of SO3. The rate is independent of the pressure of oxygen. That's another very interesting thing, that the oxygen pressure does not seem to be so critical. Of course, you have to give oxygen to the requirement of the stoichiometry. Otherwise you're not going to get SO2 going to SO3. That stoichiometric requirement has to be met. But I don't necessarily have to have a much higher amount of oxygen hanging around there. The activation energy on platinum surface is about 10 kilocalorie per mole. If you compare that with vanadium pentoxide, the activation energy is about 23 to 34 kilocalorie per mole. Obviously, platinum is a more efficient catalyst with a much lower activation energy. But we'll also see what else happens. Maximum value of 34 kilocalorie per mole has actually been observed for pure V2O5 catalyst. So this is another thing, that when we say V2O5 catalyst, if you take pure vanadium pentoxide, this is what you'll get. Vanadium pentoxide does not exist in a pure state in the catalyst. It is basically adsorbed on some other substrates which are promoters of the reaction. That's how the term promoter comes in, and that's how you get a relatively lower activation barrier because of these promoters. Now, the other very interesting thing is that the rate of oxidation of SO2 to SO3 on the surface of vanadium catalyst largely depends upon the pressure of oxygen and weakly upon the pressure of SO2. Exactly the opposite of platinum. These have very, very profound implications in terms of the industrial practice of these reactions. Can anyone tell me what could be the drawbacks of the vanadium pentoxide in terms of its practical use as compared to platinum because of this? Just read it, just see what it says.
So we would require a relatively higher amount of oxygen than SO2.
Very good. In the case of vanadium pentoxide, right?
Yes, sir.
Right. Now, obviously, if you are saying that it requires fair amount of oxygen, what you are also saying is that the SO2 concentration will relatively be lower.
Yes, sir.
Right. Obviously, by inference, that's what I'll say. What it means is that the throughput of the reaction, that means from the same catalytic bed, I'm not going to push as much of SO2 as I would be able to do in the case of the platinum catalyst, because my SO2 is relatively more dilute. Got it?
Yes, sir.
That's how profound it is. If you just read it as a statement, of course, it looks scientifically interesting, but you must also be able to appreciate, therefore, what are the implications in terms of practicing the process, and also how important reaction mechanism is. Because if I don't know the reaction mechanism, I don't know anything. I'll be shooting in the dark. So let us just try and quickly see what is the mechanism for the action on vanadium pentoxide. In fact, I struggled to get the mechanism for platinum, which I couldn't. But let me at least tell you what is the mechanism in the case of vanadium pentoxide. So you have SO2 coming in. It's picking up 2 electrons. Actually, these 2 electrons, etc., that you see are really the electrons that are coming from a variation in the oxidation state of vanadium pentoxide. Vanadium pentoxide, what is the oxidation state of vanadium?
+5.
Right. But over here, what you will see is that vanadium actually shuttles between the +4 and the +5 oxidation states. And so what's happening is that SO2 is first picking up 2 electrons, and it is obviously these electrons are coming from the catalyst, and it is forming SO2 2-, which is chemisorbed. And this is an enthalpy negative, means it's a very exothermic process. And this rate, this particular thing is very fast third order chemisorption reaction. It's not the rate limiting step. After that, what happens is that oxygen, this should have been SO2 2 minus, this stuff. Okay, that's why I've put it here. They've made a mistake over here. This oxygen is picking up those 2 electrons and it's transferring an oxygen to the SO2. Okay, so it's becoming SO3 plus O2 minus. This is the rate limiting step of the reaction. You can see slow second order reaction. And after that, what is happening is that this O2 minus is again giving back its electron on the surface to the catalyst and just going off as oxygen, O2. So that, this 2E again can pick up again SO2 and this whole process can go on. If you look at it in terms of the vanadium, this is what is happening. The SO2 plus 4B5 plus 2O2 minus is effectively going to, this is 2SO3 plus 4B4 plus, and the B4 plus is basically with oxygen getting oxidized back to B5 plus 2O2 minus. Effectively, that's what is happening. I mean, this is getting oxidized, the V4 plus to V5 plus, and this is becoming O2 minus. So when over here is written without the vanadiums, you can try to put it back in, and that's effectively what the mechanism of this process is. And so there are people, you can see Calder-Bank wrote this mechanism in 1952, long after the vanadium pentoxide process was being practiced, but it was long after that, several decades after that, that the actual mechanism of the reaction was worked out. So you don't have to wait to practice a process just because you don't know the mechanism, but it always helps to know the mechanism. Because if you know the mechanism, you can improve on the design of your process accordingly. All clear to everyone?
Yes, sir.
If you compare Peregrine Phillips platinum catalyst and vanadium, right, let us try and look at it. And these are the kinds of things that, suppose you were the owner of a company and you had to decide, what you want to do. And let's go back to 1910 or 20, when both of these processes were equally being practiced, and you have to decide what you want to do. Which catalyst should you opt for? Which technology? So these are some of the important parameters on which to judge. In terms of conversion, what was found is that the conversion tends to be higher on the vanadium catalyst. Mind you, 1899, these are the people who first came up with vanadium pentoxide catalyst. Although it was only in 1913 that it was subsequently improved upon and commercialized. Here, it tends to be lower, the conversion, and as you will see, decreases with use, means the surface gets poisoned. Investment, initially less. 5% replacement is required per year. 5% replacement of the catalyst is required every year. And in this case, higher is very high because platinum costs more, lower life and highly fragile, which means that obviously in terms of investment, the investment would be higher for the platinum catalyst. Catalyst poisoning, the B2O5 is relatively more immune to poisoning. Okay? Whereas in this particular case, now it so happens that many of the streams, they tend to have traces of arsenic. Arsenic has been found to be a poison for the platinum catalyst. And so especially if you've got arsenic in your stream, then you would never recommend the platinum catalyst. But then if your stream does not have any arsenic, you might. Okay? You might say, yeah, I don't have this problem. And you may say, well, if there are other benefits of platinum, we'll see. Another is that handling of SO2. So this is where the platinum catalyst has a maximum advantage, that you can actually take more amount of SO2 in your feed stream compared to vanadium pentoxide. So obviously the throughput of the reaction would tend to be higher when you are using platinum. Another is that, well, in terms of the actual catalyst, you need 189 grams of platinum, although nobody just uses platinum like that. Platinum is invariably put in a support. So if you add the weight of the support, then that weight is not going to be 189 grams. It will be much more than that. In this case, though, what you have is, you have a catalyst which is roughly about 14 kg weight, and in which about 7 to 8% is the weight of the vanadium pentoxide. So 92% is your promoter or your support substrate on which the vanadium pentoxide is sitting. This comparison is not fair, because in this particular case also you need to put in that support, in which case you may not find a huge difference between the two, although probably that if you have the platinum catalyst, maybe the catalyst bed would be more compact. It would have less volume. Most likely that's what will happen. Now, another thing which is very important to make a note of is that today everybody has forgotten. You say contact process, vanadium pentoxide, BASF, but there were huge litigations. Once the vanadium pentoxide had been invented by Myers 1899 as a catalyst, many people started making all kinds of different combinations on the catalyst with different kinds of supports, and there were a huge number of patent infringement cases. Someone would say, no, my catalyst is better, you are infringing on my technology, and this went on for quite some time. But ultimately BASF prevailed, and I think that everybody came around to the fact that the BASF catalyst is the best catalyst. So everybody else more or less kind of fell by the wayside compared to BASF. As I said, the main disadvantage of vanadium pentoxide, and as one of you has already pointed out, is that you need to use a more dilute SO2, because the rate of the reaction depends strongly on the oxygen concentration and only negligibly on SO2. So I therefore have to take less amount of SO2 and more amount of air. And you're not having pure oxygen, you're having air. So air has only 20% of oxygen. So you have to factor that in. And that's why it becomes so crucial. Now, secondly, another point which you might overlook, what would happen as the reaction is taking place? So I initially put in air and SO2. What happens as the reaction is going on? In terms of, let's say, the concentrations of these gases.
So concentration of SO2 decreases.
Yes. And?
SO3 is formed, so.
Yes, correct. And what else? Oxygen gets consumed. Right?
Yes, sir.
Yeah. So, if the rate of the reaction is very, very strongly dependent on the oxygen concentration, then as my oxygen is getting consumed, the oxygen in the air, my rate is going to fall off precipitously. That's the reason why I have to take less concentration of SO2 and make sure that I've got sufficient, more than enough of oxygen, so that even after the consumption of oxygen, I still have sufficient amount of oxygen left. Because if I just take stoichiometric amounts, I have had it. Because my oxygen levels will fall off very fast. Is that clear?
Yes, sir.
Always keep in mind that don't only look at one thing. Just because we are interested in SO3, don't only look at SO2. Also look at the oxidizing agent, which is oxygen. It's as important as the SO2 insofar as the reaction is concerned. Understood, everybody?
Yes, sir.
Okay. We had already gone through this plot before. Okay. All I've done is that I've put in two lines over here. If you look at this, is the place where you are getting more or less 100% SO3. Okay, is when my absolute temperature, this will be about around 700, right? This is in terms of K. So in degrees Celsius, it will be about 430-40 degrees Celsius. Correct?
Yes, sir.
Yes, sir.
And if you take this point here, where let's say something like around 60 to 65% conversion takes place. Now over here, what you can see is that the temperature is around 900 K, which means around 600 and say 30 degrees centigrade. Right?
Yes, sir.
So if you go to a temperature higher than this, you are not going to get 100% sulfuric acid unless your temperature finally is somewhere here. You will be stuck with a low conversion, and nobody will accept such an industrial process. But on the other hand, we know also that the rate of a reaction will be higher here, and the rate of the reaction will be lower here, because rate depends on temperature. The ingenuity of chemical engineers was really in balancing out all of this. If the vanadium pentoxide catalyst is so important and so great, one of the reasons is because it has been able to manage this plot of mole fractions of SO2, SO3, O2 at different temperatures. Let me ask you the question. What is vanadium pentoxide? What is the state of matter? What is it?
So solid.
Solid, right? Here is the fun. We saw that around 400, 420 degree, if you can reach that temperature, you will more or less be able to get quantitative SO3. We saw from that plot. Okay? Now, so I can of course go to lower temperatures and it will be still 100%, but there's no point, because I also have to look at the rate of the reaction, right? Now, on the other hand, if we try to do the reaction at 650 or so, again I have a problem. Now my problem is not the rate of the reaction, my problem is the conversion of the reaction. Okay? Because my conversion is going to drop. And you have seen how steeply it drops with temperature from this plot. Okay? So look how steep it is, how it's falling off with temperature. So this is the dilemma. What happens is that, and this is what BSF presumably would have said, that look, if 400 degrees or thereabout 400 degrees Celsius, I am getting more or less 100% conversion, then let the lowest temperature at which I am going to operate be around that temperature, around 400, 450 degrees centigrade. And since I have got this problem of conversion falling off very steeply at higher temperatures, I don't think that I would like to go exceed a temperature of 600 degrees centigrade in any case. So what they have done is that they have played around in this kind of a temperature range. It's a temperature range, and we'll see the clever stuff that has been done. Now look at this. The melting temperature of V2O5 is around 400 degrees centigrade or thereabouts. Okay, so the vanadium pentoxide under those conditions is a liquid. So actually the reaction is taking place with the liquid state of vanadium pentoxide, not with the solid state. Secondly, they use a lot of these are the carriers. The liquid is forming a film, getting absorbed on these kinds of carriers. They are all things like, it can be kieselguhr, silica, alumina, stuff like that. But what they also found is that along with this, when they add certain other constituents, the basic activation barrier comes down. We saw that from 34 kilocalorie per mole, it tends to come down to something like 25, 24 kilocalorie per mole. And that is promoted by certain alkalis and some other things. All the cleverness, the trick is all around this. Everybody knows vanadium pentoxide, V2O5, you can buy it in the shop. But the name of the game is how to play around with all of this so that you can minimize the activation barrier, lowest activation energy, and you can speed up the reaction, and also that your catalyst will not degrade. Now, another very, very interesting thing is that, 620 degrees is the temperature at which vanadium pentoxide starts degrading. Okay? Whereas less than 400 degrees centigrade, it solidifies. So the temperature at which it remains a stable liquid is very nicely in tune with this. In other words, the thermodynamics of the SO2 to SO3 process and the behavior of vanadium pentoxide as a catalyst and its physical form are almost like made for each other. They are a made for each other couple. It is just too beautiful. And if vanadium pentoxide has become such an exceptional catalyst, it's because of that reason. By the way, let me ask you the question. What is the advantage of having vanadium pentoxide as a liquid compared to solid?
Sir, as a liquid, it has the ability to absorb or adsorb the gases around it much better when it is a solid.
Brilliant. I will now use the term absorb in the catalyst. Okay? Because you see, if I've got a solid, the absorption will only take place on the surface. It's not going to penetrate. And so unless I've got almost like a monomolecular layer of the catalyst, which is very difficult to get, my utilization of the vanadium pentoxide is only as good as the surface area of the catalyst. Whereas when it's a liquid, the gases may be able to penetrate deep inside the catalyst. So the utilization of vanadium pentoxide would be much better. That's exactly what you have said, and that's wonderful. So I hope you can see how well tuned everything becomes. And another thing, the reason why I'm stressing to you the nuances of what makes an industrial process a great process. It's not just saying vanadium pentoxide catalyst, this, that. No. It's the beauty, the elegance lies in the detail. Like I remember we were doing a reaction with paranitrotoluene. The stuff is a solid, and we were trying to do a benzylic bromination. That CH3 was going to become CH2Br. And we wanted to do it without the use of a solvent. That was the desire. Now the interesting thing was that the reaction we were carrying out at around 70 degrees centigrade, and that paranitrotoluene melted around 55 degrees centigrade. So if you don't know that, or if you do not anticipate that, like a fool, you'll go and put solvent over there when maybe a solvent is not required. It's already a liquid. And in fact, we could do the whole reaction 100% conversion without using any solvent, because we were using the molten form of the substrate. So what you need to consider is the reaction temperature. What is the temperature at which you're doing it? What is the physical state at that point of your catalyst, of your substrates? Keep that in mind. All clear to everyone?
Yes, sir.
Now, let me ask you. Now, I know that if I do this reaction at 600 degrees centigrade, of course, I'll get a good reaction. But we have seen what is the problem with the conversion. Okay. So, what should we do? We can play in the temperature range of, there are a few things. We can play in the temperature range of 400 to 600 degrees centigrade. We can, we know that the reaction of SO2 to SO3 is exothermic. Okay. So what should we do? How should we carry out the reaction? Or what would you like to do to carry out the reaction? Would you like to carry it out isothermally? And if so, at what temperature? Or would you like to carry it out adiabatically?
So maybe adiabatic, the temperature should be such that, so that since it's an exothermic reaction, so heat would be released. So the temperature should be adjusted such that it does not exceed 620 degrees for the catalyst to degrade.
How would you make sure that it doesn't exceed?
So after some time, like when we see the temperature approaching 620 degrees, the temperature around which the catalyst degrades, we may just turn off the heat supplied.
Brilliant. You said turn off the heat. Huh?
Or lower it, supplied externally. We can lower the heat supply.
But heat is being generated by the system.
Yes, sir. So it is being generated, and we are also initially supplying it externally so that the particular temperature is reached for the reaction to go on or to begin. And once we
I think, broadly what you're saying is correct. And after some time, turn off the heat, and make sure that catalyst remains in desired temperature range. That's what you're trying to say, right? Correct?
Yes, sir.
Okay. I mean, you're almost right, not fully right, but I think it's brilliant. You remember that I was telling you that one extreme is adiabatic and another extreme is isothermal, and engineers always like to play a middle game. So you're just trying to see how you can look for compromises. Exactly as you said, they start with a certain temperature. They allow the reaction to take place, up to a certain point, and for which you can do that in several ways. I can take my catalyst bed, the height, diameter, etc., so that what is the amount of catalyst to amount of substrate, etc. The other is also I can vary the flow rate of my substrate, through the catalyst. So if I see that the temperature is rising, I can just make it go a bit faster. If I can't play, obviously I can't take out catalyst suddenly, but I might be able to play with it. So what I do is that I let the temperature rise adiabatically, just like you said. And maybe I reach a temperature of around close to 600 degrees. Now, what happens also is that because I've done it adiabatically, and because I've let the temperature rise, so the quality of my heat is very high, very good. I've got 600 degrees centigrade temperature. Whereas, suppose I did it isothermally and I kept extracting heat. One is that I would get a very poor quality of heat to come out. Okay, and the second is that it would affect the rate of my reaction. Third is, suppose I am letting it go up to 600, but I know that the conversion is only about 60% at that stage. But why am I not bothered? Why am I still allowing it to go up the temperature to 600?
So the temperature decrease will be gradual, sir, rather than a drastic decrease, sir.
Temperature decrease?
Yes, sir.
Which
after we turn off the external
when I'm doing
heat.
it adiabatically, my temperature is increasing. Where is the question of decrease?
So after we turn off the external heating, sir.
You want it to slowly again come down. Huh?
Yes, sir. Yes, sir.
See, what happens is that when I'm in the early stages of my reaction, the equilibrium actually doesn't bother me much. The equilibrium becomes a more and more serious issue as I'm going to higher and higher conversion. Let's say I'm doing the reaction and I'm reaching a temperature close to about 600 degree temperature, let's say initially, and I'm getting 60% conversion. I'm okay with that because in any case, I'm far away from equilibrium. Okay, I've not reached equilibrium at that point, and I get a very high quality of heat, and I'm taking it out. I'm not letting it just go. The temperature is not decreasing gradually as you might think. There is a forced extraction of heat with the help of heat exchangers. I might be passing water and the heat is extracted out and I'm generating high quality steam. You understood? I've reached about 50-60% conversion. I'm okay with that. Now what I do is that after I've reached that kind of a conversion, I forcibly cool it down, not just slowly heat dissipating to atmosphere. There are liquids, which are used to, or gaseous streams, which are used to do a cross exchange of heat. Something is getting heated, something is getting cooled. And initially, I get such a good quality of heat that best thing to do would be to pass water, and the water will become steam. And I can run a turbine and generate electricity with that steam. In fact, sulfuric acid plants are cogeneration plants, so I can actually generate electricity. You never run a sulfuric acid plant only for making sulfuric acid. You run it also to harness electricity. When I'm cooling it down, I will cool it down, to the initial state. So let's say I was at around 400 degrees. I will come to around 400 degrees, which I'm doing with the help of a heat exchanger. When I'm doing this cooling, I'm doing it outside of a catalyst bed. I'm not doing it in the catalyst bed. And so nothing can reverse when I'm doing a cooling. Whatever yield I got at this point, the yield will remain more or less the same here. Now I introduce it into a catalyst bed, and I allow it to further react. Again, after some point, I again play this trick. Again, I allow it to react. So I'm doing adiabatic, then cooling through heat exchanger, adiabatic increase. And what am I doing? I'm slowly approaching my temperature of 400 degrees centigrade. Now, when I come to 400 degrees centigrade or thereabouts, then I may not be able to achieve this kind of 100% conversion or greater than 99% conversion. I may get stuck at about 96%, 97% conversion. So at that point, I play another game. What is the other game I can play? At that last point, what else can drive my equilibrium? Besides temperature, how else can I drive the equilibrium to the right?
Removal of product.
Fresh.
Wonderful. Sweep out product. Okay. So what you do is that at some point here, before it goes into the last bed, I pass it through sulfuric acid and all my SO3 gets absorbed and only my SO2 and the remaining air, etc. is there. I might again charge it with more amount of starting material and then I pass it through my fourth bed. So effectively, I've driven the equilibrium to the right by an absorption process before it enters the final stage of conversion. We will continue from here tomorrow, all right?